Okay, welcome back. I want to talk about configuring Timer0 to use the PWM, the pulse width modulation, on output compare pin 0B, which is on pin 9 on the microcontroller. You can see here my pin's not working. Okay, pin 9 PD5. So we're going to have to configure port D5 as an output pin because we want to use the output compare 0B as our PWM output. So what we'll do is configure the timer 0 so it starts at 0 and starts counting up. When it starts at 0, the value on output compare 0B will go high. It will count up until it matches the output compare register 0B, and at that point, when there's a compare match, the value on the pin will go low, and then it will continue counting up until the output compare register 0A. At that point, the value on the pin will go high, and the counter will reset back to 0 and then continue counting up to OCR 0B again. So we have timing diagrams in the data sheet, and like we said before, there are four different modes for the waveform generation modes. I lost the timing diagram. Here we go. So this is our CTC mode. We want fast PWM mode. And in our fast PWM mode, here we go, right here. Okay, so we have a fast PWM mode, and the counter is going to start at 0, and it will count up until it has a compare match. So on here, we're going to configure OCR 0B, and that will determine the width of the pulse width. So it'll count up until it has a compare match with OCR 0B, and the pulse will go low at that point on the output pin. It'll continue counting up until it has a compare match with OCR 0A, and at that point the counter will reset to 0 and the pin value will go high. So if we have a higher value in OCR 0B, we're going to have a longer pulse width, but we need to keep that value less than the OCR 0A so that we can have a PWM signal, a pulse that goes on and off for a short time. And what we'll do is we'll set the PWM frequency. We'll do one that's appropriate for a servo motor. So a servo motor expects a pulse width frequency of about 50 hertz. And 50 hertz is 50 cycles per second. So if I do 1 over 50, I can get the period of time for each cycle. And so 1 over 50 is 20.02 seconds, which is 20 milliseconds. So we need to set a OCR 0A value so that it will reset the timer every 20 milliseconds. Then the pulse width for the servo motor, the motor in the center position on a standard servo motor is about 1.5 milliseconds or 1500 microseconds. So we'll set the output compare register 0B so that it will take 1.5 milliseconds for the timer to count from 0 up to that value. And then the remainder of the 20 milliseconds, it'll count from the OCR 0B up to OCR 0A register. So we have to figure out what values to use in the OCR 0A, the OCR 0B, and also the clock select bits. We have a 1 megahertz I/O clock by default, and the CPU I/O clock is 1 megahertz. So by default, it takes 1 microsecond for each count on the timer 0. And 1 microsecond, you could only count up to 256 microseconds at a maximum, which is not nearly a long enough time. We need to count up to 20,000 microseconds to get a frequency of 50 hertz. So we have to divide our clock value by a number that will allow us to count up to 20,000 microseconds before the timer overflows. And remember our values that we had for the options which we'll look at right here on our little table. So the options we have is the CPU clock I/O divide by 1, that's no prescaling, or divide by 8, divide by 64, divide by 256, and divide by 1024. So if I divide the CPU clock by, let's say, 1024, it's going to take 1,024 microseconds for each count. And I need 20,000 microseconds, right? So if I take 20,000 microseconds and divided it by 1,024, we get about 19.5 as a result. So that means it would have to count from 1,024 microsecond steps from 0 up to about 19. And then it would have to reset back to 0. So we want a much higher value than 19 because 19 doesn't give us much resolution at all. So the next value option is 256. So if we take 20,000 and divide it by 256, and then we get 78.125. So we round it off to 78. So that's a possible option. The next option was a divide by 64. And if we divide 20,000 by 64, we get 312. Well, that's not going to work because we can only count to 255. So we're going to have to go back to the 256 option. So we're going to set our clock to divide by 256. And then if we count to 78, 78 times 256 is approximately 20,000 microseconds. So let's go back to our program here. So I've already got this written because I didn't want to spend a lot of time on the video doing typing. So the 256 option here is a 100 on our clock select bit. So we need to set our clock select bits in TCCR0B to 100. So we have that here on our TCCR0B here. Our clock select bits are 1, a 0, and a 0. So that'll make the CPU I/O clock divided by 256, and that will be the clock source for timer 0. Now the waveform generation mode, we wanted it to count from 0 to 255 and then reset to 0. So we need to set the waveform generation mode so it will do that. And that will be here under TCCR0A. Oops, did I miss it? There it is. Okay. So TCCR0A. And we want to count from 0 to 250, or 0 to the OCR0A register, which in this case, this one, the top value is OCR0A, so we have a choice of the CTC mode or the fast PWM mode. So the fast PWM mode is a better option, mostly because if you update the output compare registers, they get updated at top where the timer is overflowing back to 0. That way, if I put a value in that's smaller than the current timer value, it doesn't get updated until the counter reaches the top, the OCR0A register. Therefore, my counter doesn't miss the compare match value and not get reset and continue counting all the way to 255, which would cause a major glitch in the system. So the better option for us to use is a 111 for fast PWM, and the top value for the count will be OCR0A. And we said that we were going to set that to be 78. So that was a 111. So we need to set the WGM bits to a 1 for WGM02, which is in TCCR0B, then a 1 for WGM01, and a 1 WGM00 in TCCR0A. The compare output mode bits, we want it to go high at 0 and stay high until it has a compare match with OCR0A, and then go to low, and then, did I say that right? A high at 0, stay high until it has a compare match with OCR0B, and then go low until it has a compare match with OCR0A, and at that time the counter will reset to 0, and the pin value will go high again. So we need to set the compare output mode bits for that. And you can see compare output mode 0. So we're using fast PWM mode here. So we want the right table here. So we have fast PWM mode, and we'll compare output mode be COM0 B1, COM0 B0. So that timer 0, B1 and B0. So we want to set it on 0 and have it clear on a compare match, right? So clear on OC0B compare match and set at top, which is when the timer will overflow to 0. So we need a 1, 0 in COM0B1 and a COM0B0. So COM0B1 is a 1 here, and COM0B0 is a 0 here. And that will set it. So that's a non-inverting PWM signal. So we now to time this, one way we can do the timing on this is set the output compare interrupts for 0A and 0B, and then have a simple dummy routine for it to go to, and we can set a breakpoint so that whenever the interrupt is triggered, it goes to the breakpoint, and then we can use our stopwatch in the simulator to time how long it takes to get there. So what I did is I set the OCIE 0A and 0B, that's under timer 0 and the TIMSK register. So you see OCIE 0B and OCIE 0A in those registers. So I put those two values into temp, and then I output it from temp to the TIMSK register here. And then I had to set the interrupt vectors for the output compare 0A ISR and output compare 0A ADDR. That's in the include file. And then the output compare 0B ADDR. So I remember where we find these are at the end of the include file, the names for those interrupt vectors. So OC0A ADDR, OC0B ADDR are defined in the include file at the very end. Okay, so we use those names for our org statements to locate the rjump instruction, so the relative jump instruction to an interrupt vector that we have down here named OC0A ISR. Because we're just using them for timing purposes, we can make them both jump to the same interrupt service routine. It won't matter. And then on those instructions, I right-clicked on there and I said toggle breakpoint. So I set the breakpoints on both of those interrupt vectors. Okay, we're ready to simulate our program now. We should watch for the port D2 value changing as we're counting, and we want to use the stopwatch to time our program to see how long it takes to count up to the OCR0B and the OCR0A register. So the goal was 1500 microseconds for OCR0B and 20,000 microseconds, which is 20 milliseconds, for the OCR0A register. So we started the simulator. I'm going to run it through full speed ahead a couple of times here. And then I'm going to go to the OC0A register, and I'm going to reset the stopwatch here. So we'll run it full speed ahead until it comes back to the same breakpoint. And again, we should hopefully get around 20,000 microseconds. So I'm going to go to OCR0B and then back to OCR0A. And we got 20,224 microseconds. So that each count on our timer takes 256 microseconds because we're using the CPU clock divided by 256. And the CPU clock is 1 microsecond per count. And when you divide the CPU clock by 256, it takes 256 microseconds per count. So basically what that means is if we subtract 256 microseconds from the 20,224, we're going to be closer to 20,000, a little bit under, but closer. So we can just subtract 1 from 78 and we'll be closer to 20,000 microseconds. now let's check our timing on OCR0B before we go back and make any edits. So I'm going to run it full speed ahead. And I made it think I changed something. Okay, let's try this again. Okay, I'm going to run it full speed ahead. I'll do it a couple times here. Okay, now I'm going to reset the stopwatch. And now we're going to see how long it takes to count. Actually, we want to start at OCR0A. So I'm going to go to there, reset the stopwatch again. And I want it to take approximately 1500 microseconds to get to OCR0B. So we run it, and we're at 1792. So that's 292 microseconds longer than we want. So again, if we subtract 1 from our OCR0B register, that means it's going to count 256 microseconds less time, because it's 256 microseconds per count, right? So that'll put us a lot closer to 1500 microseconds. So let's go ahead and make that change, and then we'll test it again and see how close we are. So from this one is a really small value, it's at 6. And by reducing it to 5, I mean, that's almost a 20% reduction in our time. So that's pretty low resolution. We don't have very much accuracy on our control for the pulse width, which means basically to get good resolution, we need to go to the 16-bit timer and have a much higher resolution. Okay, so I reset or change the values from 78 to 77 and 6 to 5. I'm going to assemble it again. Okay, we assembled with no errors. I'm going to start the simulation, and we'll run it full speed ahead until we get to the OCR0A register, as you do a couple times here. And then I'm going to reset the stopwatch and run it again until we get back to the OCR0A. So there and there. And now we're at 19,968. So we're only 32 microseconds short of 20,000 microseconds. That's pretty close. It's plenty close enough for a servo motor. So now let's see how long it takes to get to the OCR0B from this point. So I'm going to reset the stopwatch and count how long it takes to get to OCR0B. And it's 1536. So it's 36 microseconds longer than we need. But that's really close. 36 out of 1500 is not too bad. So our servo position will be close to centered, and our servo frequency is going to be close to 50 cycles per second. And again, we have quite a bit of tolerance. It doesn't have to be exactly 50 hertz. We can do 48, we can do 55 probably, and be okay. So our timers are pretty good. Now let's look at our pin D5 here, and we watch and see if it's making the change. So you can see it just turned on here, and then run it again, and it turned off. Run it again, it turned on. Run it again, it turned off. I'm going to, well, this is going to take a while. Let me see. If I auto step, it's going to take way too long to simulate, because it takes 256 counts on our simulator to count once on the timer. So that's not going to work. We'll be here all day waiting for that. So, but we can see it's turning on and off. And we checked with our stopwatch, and we saw the timing was pretty good. So I think we have a pretty good program here, except we have very low resolution. Now what we could do is add a push button, or 2 push buttons, one to increase the OCR0B register value, and one to decrease the OCR0B register. And that will give us control over the pulse width on our signal. But before we do that, I think it would probably be a good idea to go to the timer 1 and do that, because we have such low resolution on here. We don't have very much control, and it's probably not very usable for a servo motor, because it'll be really glitchy. One push of the button and it's going to jump several degrees. So it'd be better to go, and we'll do another video at a different point in time while we're using timer 1, and we'll do the PWM. Using timer 1, we'll have much higher resolution. Okay, so I think we're good for this video. We simulated it. We saw the pin changing on pin D. The pin D I didn't mention. This is set, I did a set bit and I/O register, DDRB. So that configures pin D5 as an output pin here. And we have the stack pointer configured, so the program counter value gets pushed onto the stack every time it enters our little interrupt service routine. This interrupt routine is really doing nothing. It's just kind of a placeholder. So I think we're good for now. Thank you for watching, and we'll continue on making more videos. Have a good day.